Hi, my name is John Fortner, and this is my video report for Lab 4, Circuits and Capacitors. Lab 4, Circuits and Capacitors investigates how variables in a circuit, such as resistance, potential difference, current, and capacitance, interact in RC circuits. The main focus of the lab is on the rate of charge and discharge of a capacitor. This lab relies on the laws of conservation of charge and energy, from which a variety of laws surrounding circuits are derived, such as the node rule and the loop rule. So in this lab, we observe the rate of discharge of a capacitor connected in series to a light bulb as measured by a voltmeter connected across the capacitor. We derive from a differential equation, a linear equation, relating time to the potential difference, which is the natural log of delta V over delta V naught is equal to negative T over RC. We then use measurements of the potential difference over time to calculate the RC constant for the RC circuit. Our light bulb has a resistance of 30 ohms. Our capacitor has a capacitance of 0.2 farads, and our capacitor was charged with a 9-volt battery. So during the experiment, we measured the potential difference across the capacitor at constant periods of time. So this is a plot of the time by the natural log of delta V over delta V naught. And from it we see this very linear plot, and this line of best fit is described by this equation right here in the tiny box, y equals negative 0.1667x plus some constant. And from that, we have the negative inverse of the actual final value for our RC constant, which you can see calculated up here. So as we saw from our Excel sheet, we obtain a value for our RC constant of 5.9988 seconds. And this constant, by the way, is a measure of how fast or slow the capacitor charges and discharges. The greater the RC constant, the slower the charge or discharge of the capacitor. So some additional questions. What if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it have affected the circuits you hooked it up to? So a real ammeter would have had some amount of resistance, which would contribute to the overall resistance of the circuit. And we could confirm that the ideal simulated ammeter in our model did not have any resistance because the potential difference across it was not different from what we would have expected. It was 0. So even some negligible amount of resistance in a real ammeter would have had some effect on the flow of current through the circuit, and also on the potential difference across the ammeter in the circuit. And what if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistance in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? So first of all, if we had 0 resistance in our circuit, then we would have an undefined value by our equation. So considering it as a limit, we would see that we would be approaching an infinite value, and so our model would predict that a capacitor would be charged instantaneously. And in real life, the capacitor would charge very quickly, but there would be some amount of resistance in the wire of the circuit that would contribute a small, but nonetheless present, decrease in the efficiency of the charging process. That's all. Thank you very much for watching.